Good morning, dear friends. The topic of magnetic induction produced by current carrying conductors. Yesterday's class and session was on straight conductor, and today let us take all the other possible cases as well. In such cases, the very popular topic is the magnetic induction produced by a circular conductor carrying current. Here I have shown a geometry, and do remember this is a kind of 3D geometry that is required, and this is the circular conductor, radius capital R, I is the current carried by the coil in an order. We call it either clockwise or anti-clockwise order. Remember, if we are talking about straight conductor, we say direction. In the case of circular conductor carrying current, we speak of order of the current. Now here I have shown an axis like x dash, supposing I call it as an axis, we call it as the axial line. What is that axial line? See, circular conductor, suppose this is xy plane. If I consider the plane of the board as xy plane, this is how I held the circular conductor. This happens to be the YZ plane, and now it is held such that x-axis becomes the axial line, the line passing through the center and perpendicular to the plane of the conductor is what is taken to be axial line. And here I considered a point P on the axial point at a distance x from the center C. Now I have given the expression, a very popular expression. You have derived this expression. B at this point P is mu naught I r square by 2 times r square plus x square whole under, whole of 3 by 2 is the index. Now along with the magnetic induction, see, we will consider now this circular conductor as a magnetic shell. It is acting as a dipole, and therefore we also give a result for the magnetic moment of the dipole, and that result is capital M. If I am using it as a symbol, current times the cross section will give you the magnetic moment. This is for magnetic induction and this is for magnetic moment. For both of them, the direction is essential because of the vector nature. Now, how to give the direction of B at any axial point due to a circular conductor carrying current? We are again using the same right hand rule. Yesterday's rule was for a straight conductor, in which we said in the right hand grip, thumb representing the direction of current and the curl of the fingers representing the magnetic flux. Accordingly, we have drawn a tangent and found the direction either inwards or outwards, such examples. Now, same right hand rule with a small difference for circular conductors or arc shaped conductors. And the rule is that in the right hand grip, the curl of the fingers represent the order of the current, then thumb shows the direction of magnetic induction at axial point. Got it? We are now not saying the direction of current. Remember, I have told you in the case of these cases, it is the order of current, clockwise currents, anti-clockwise current. Therefore, the curl of the fingers representing order of the current, thumb shows the direction of magnetic induction. Here, as I have told you, this was the conductor held in this YZ plane. Now, accordingly, it is carrying this kind of anti-clockwise current that you can see here. Suppose if it carries anti-clockwise current, look at my finger, it is towards your right hand side, right? Supposing if it carries clockwise currents, then it will be towards your left hand side, and that is what is now I am representing at P as the vector. So this is the vector at the P. Now what about the direction of magnetic moments? Magnetic moment M bar vector we will write now parallel to B bar vector. We will mention. In such case, do remember, this will be helpful for us in our next topic, electromagnetic induction. See, This is a circular conductor. Supposing it carries anti-clockwise currents, my thumb is upwards, right? So now at any axial point, the field is upwards. So the magnetic moment is also upward, means that this phase at the bottom is acting like a south pole, and at the top phase is now acting as north pole, because that m bar vector is from south pole to north pole, and that is why. So the point is m bar vector parallel to d bar vector, and depending upon the direction. So in the direction of b bar, first we get south pole and then we get north pole. Now I would like to show one or two important results from this expression. You please write along with your teacher and try to practice it, and so that you can do examples faster. Now I am writing B at center of the conductor. What will be the induction? Center of the conductor means x equal to 0, because the distances are from the center. So for that value we get B at C at the center, mu naught I by 2R. Again, one more time, please look at this denominator term. Yesterday when we talked about the straight conductors, in the denominator there was pi term. When you are writing circular conductors, there is no pi term in the denominator. And also one more time, here we have 2 points. One is an axial point at distance x, and the center also an axial point for which x equal to 0. Now when we comparison of B at P with B at C, then I am writing this ratio B at P by B at C. I have done that calculation and I am directly giving you the result. Remember, 1 by 1 plus x squared by r squared whole power 3 by one more reduction that we can do for this x very much less than r. What is meant by very much less? Even in the last classes when we were discussing about the percentage changes, we told any numbers less than like 2%, 3% of that order, those changes were like small changes. Here also any numbers that are given and there happens to be like 1%, 2, 3%, then they are taken to be the smaller values. So for x very much less than r, we use that approximation, the binomial approximation. You remember, I suppose, right? Accordingly, the result will be B at P is, right, B at C times 1 minus, this will 3x squared by 2r squared will be the result. Because this 1 plus x squared by r squared, when rises to the denominator, it becomes negative term minus 3 by 2. And then I have used that binomial approximation. So this one is also an important result. I will make use of this and for doing examples in a shorter time. So this is how we have done with the case of a circular conductor. Now let me take the case of same expression like here, mu naught I by 2r. Because as I told you, we may think that it is more number of formulae. No, to show you that I am giving you one more result, that let us take the case of a B due to orbiting charge. In current electricity we have told that a charged particle in orbital motion, then the orbit as a whole acts as a current loop whose current is given by I is equal to charge times frequency, otherwise qv by 2 pi r, orbital velocity v, r for radius, this is the thing. If now I am substituting I is equal to qv by 2 pi r, right? So even an orbiting charge will produce magnetic induction, and that magnetic induction we are writing at the center. So B at C is equal to the same expression, mu naught I by 2r, and therefore this becomes mu naught I by 4 pi r square. Mu naught qv by 4 pi r square. This pi r square we can take it as the area of cross section. One more time you will see all different, B proportional to V result, B proportional to 1 by A result, right? From this expression you can deduce them. Comparison of inductions by different charged particles due to orbital motion, different velocities, different sizes, different radius or different areas of the orbit and all. So this is one. Similarly, let us also write the case of orbiting charge what will be the magnetic moment that is produced. Again, we told that magnetic moment M is current times the cross section, I times pi r square. Again, I am using that I here. So, what is that expression? Q V R by 2. Magnetic moment M due to orbiting charge is Q V R by 2. Supposing if I multiply numerator and denominator by the mass of the particle small m, then this mvr becomes angular momentum. You remember that simple statement. mvr becomes angular momentum. Therefore, this is ql, denominator, m term also appears. So, this is ql by 2m. This is magnetic moment and this is angular momentum. And one popular topic is there, I think you all remember that, m by l, the ratio of magnetic moment to angular momentum. If you take, this will be like q by 2m, and this is called gyromagnetic ratio. Gyromagnetic ratio. Now this is purely a characteristic of, you can see, charge of the particle, and the denominator has mass of the particle. So the gyromagnetic ratio depends only on the nature of the particle. For electron, for proton, for alpha particle, comparisons of this gyromagnetic ratio will be a very tough NEET or CET example. But do remember, as I have told you, the basis is that B at C mu naught I by 2R, substitution of that I that we have used for orbital current, and hence also the magnetic moment. Here also comparison of magnetic moments with respect to velocities, with respect to angular momentum. So this is a topic of very great importance. Now, having said about these results, let me now make a small change. Instead of circular conductor, they may give some, most of the times what we see is circular coil. Circular coil. And what difference it makes? In the case of a coil, we have more number of turns of same radius. So the conductor and coil, the difference is the number of turns, and therefore even in the results, a simple difference would be, I will multiply with n, the number of turns of the coil, number of turns in the coil. Even here also I will just say n. Here also I will let magnetic moment NIA. So that is the difference, a small difference between circular coil and conductor. Circular conductor, the expressions for magnetic induction, expression for magnetic moment, and also rules for finding the direction. Now, one or two simple examples. To begin with, I have shown an example where P and Q shown to be concentric coils. Concentric circular coils, common center. The data is radius of P 5 cm, radius of Q is 10 cm. Number of turns in P is 20 and Q is made up of some 30 turns. Now the question is, at the common center, initially the magnetic induction is 10 millitesla. When the order of the current in the Q is reversed, it is found to be 13 millitesla. Now the question is, find the ratio I1 by I2 carried by the coils P and Q is the question. Now immediately first when we read the question, what is our take? Initially at C, the magnetic induction is due to both by P and as well as Q. Magnitude and direction, remember now we should make use of our right hand rule. It was 10 millitesla, and when current is reversed in Q, it says it becomes 14 millitesla. So what does it mean? Initially both of them were carrying currents in opposite order, and hence it was B1 minus B2. Net magnetic induction increased means what happened? Earlier direct order of the currents were opposite. After reversing the current in Q, now the orders are same order current. Therefore, now here, if I consider B1 and B2 due to the P and the Q, this is due to the P and this is due to the coil Q, then immediately what is that expression that you get? B1 minus B2 is equal to 10 millitesla, and B1 plus B2 is equal to 14 millitesla. Since we have given expressions for B1 and B2 at the center, mu naught Ni by 2R expression, so that will give you these results. Mu naught by 2 common term. So here is N1 I1 by R1 minus N2 I2 by R2. Similarly, the second term would be B1 plus B2, here also a positive sign, right? Now when you take the ratio, when you take the division of these two, so what is that you get? 10 by 14, 5 by 7. Now we know all the values of N1 and R1 and N2 R2. I have given that numbers. It will be 4I1 minus 3I2 by 4I1 plus 3I2. The result gives you I1 by I2 is equal to 9 by 2 is the answer. Now the same example, instead if you change it like, see, for what ratio of currents I1 and I2, this common center will be a null point. Null point means net magnetic induction being 0. Then what will be the condition? Then that condition will turn as, yes, B1 by B2 equal to 1. Then the ratio of B1 by B2, here we have already given expressions for B1 and B2, right? For the null point B1 equal to B2, and of course, obviously they are anti-parallel. So B1 by B2 is equal to 1, including direction if we have read. So that expression will be like -1, saying that they are in opposite direction. So B1 by B2 is equal to 1 will give you the required result. Supposing N1, N2 are given, N1, N2, I1, I2 given, you will be asked the ratio of R1 by 2. Now you will see here, what is that B1 by B2 term you get? This is N1 by N2, I1 by I2, R2 by R1, right? Any of these, among these three, any two ratios are given and you are asked to find the third ratio, like that. Circular coil. Carrying current produces an induction of 75 microtesla at its center. Now, the coil is rewind such that number of turns are doubled. Find the new induction. When you read the question, find these keywords as rewinding, number of turns doubled, changed. So this is what are the keywords. Now where to begin with? No big thoughts. If the expression at B at center is equal to mu naught Ni upon 2R is our fundamental, there we begin with. Of course, it is only rewind, no change in the current carried by the coil. Of course, it is not mentioned in the data, but it will be understood here because nothing is said about the current. Therefore, here you can say mu naught by 2 and I, all are constant terms. Therefore, I will use B proportional to N by R. B proportional to N by R. N for number of terms and R for radius. Now here it is the case of rewind. Rewinding, what happens? If the number of turns increases, radius decreases or vice versa, right? Suppose a bigger coil, if it is made into a smaller coil, then the number of turns naturally increases. So here, this N and R, how they are related? N proportional to 1 by R. Now, in the given example, it is the data in terms of number of turns. Therefore, I will substitute for R, then you get B proportional to, of course, numerator is N and this R becomes 1 by N. Therefore, the result will be B proportional to N square. B proportional to N square, and hence the final value B2 is equal to N2 by N1 whole squared times B1. Of course, it is given to be doubled number. So N1, N2 is 2N1. So our answer is 4B1. B1 is given to be 75 microtesla. So new induction will be 300 microtesla. One more time, reading the question to the fullest is very important. Supposing the question is what is the new magnetic induction, answer is 300 microtesla, but the same asked as what is the change in magnetic induction, then the answer would be like 225 microtesla. In this example, what you have seen is that after rewinding, we are comparing the magnetic inductions. In the same case, supposing if you have to compare magnetic moments, then again we write our expression for magnetic moment. M is equal to NIA. M is equal to NIA, N for number of turns, A for cross section, which I will write it as pi r square, and again R proportional to N, because it is the data in terms of number of turns. Same example, if it is said that it is rewind, that the radius of the coil is changing, then N will be converted into R, right? So such common sense things you try to follow. R proportional to N, therefore I will write M proportional to, this one is N and this one is R square, therefore this is M proportional to N by N square, which will give you M proportional to N only. So moments comparison, then M proportional to N, I'm sorry, right? This is 1 upon N, I'm sorry, right? M proportional to 1 by N. The result earlier was B proportional to N square, the comparison of magnetic inductions, and the comparison of moments you will see M proportional to 1 by N, and inversely proportional result. Again circular coils carrying currents. Earlier it was the case of concentric coils, but this time the example is like this. Two circular coils P and Q, each of radius 10 centimeter. They are held one in another such that their planes are perpendicular to each other. The plane of the coil of P is perpendicular to the plane of the coil of Q, is the key word here. P carries a current of 3 amperes and Q carries a current of 4 amperes. Maybe order may also be given, that they are carrying currents in the same order or opposite orders may also be there. Now the question is that what is the magnetic induction at this common center is the one. I simply said circular conductors, so here number of turns is 1. Now here you see, for P, what will be the magnetic induction? For P, the magnetic induction will be mu naught I1 by 2R1, and for Q we will be writing it as B due to Q is mu naught I2 by 2R2. Now let us use our right hand rule. We said for the direction of magnetic induction, the circular coils, right hand rule, order of the current represented by the curl of the fingers, thumb representing magnetic induction. Use that. Supposing if it is for P, I am writing P in this plane, because both planes are perpendicular to each other. For this plane, if this is what is the current that is carrying, you will get it as downwards, vertically downward field. And for Q again it is carrying some light. So this is what is the current, clockwise current that are shown. Then this is the magnetic induction which is towards your left hand side. Therefore, if you draw those vectors, this is BP bar and this is BQ bar, and you will find the angle between them is 90 degrees. Angle between them is 90 degrees, therefore net induction at C is equal to root of B1 squared plus B2 squared, that is B due to P and B due to Q. All the common terms, I just write it outside. This is mu naught, 2 is a common term, R is also a common term. Therefore, this is mu naught by 2R times, you will get it as I1 square plus I2 square. A substitution 4 pi 10 rise minus 7, 2 into R given to be 10, therefore it is 20. Don't forget this submultiple centimeter into meter times I1 square and I2 square. I1, I2 values are given to be 3 and 4. This number is 5 Therefore, this is 20, 20, this is pi into 10 raised minus 5 Tesla. You are getting at the common center. Right? So one coil or more number of coils, look for the orientation of the coils, find the magnetic induction at a given point due to the individual coils, and then we will take the vector addition. Supposing in the same example, instead of this kind of this thing, small change I will make. Here I have shown the angle to be 90 degrees, right? Instead of 90 degrees, right? Because this has been a question asked once or twice in our competitive examinations. Instead, supposing I said these are two circular coils, same radius of course. Earlier we said the planes of the coils are at right angles, but now I say theta is the angle between the planes of the coil. Theta is angle between planes of the coils, and supposing it is not 90 degrees, because already we did the case of 90 degrees. Now in this case what happens? Again the rule goes, we have to write B1 bar and B2 bar along with right hand rule. Right hand rule, when we are writing, the order of the current is what is a very key point, right? Now if you use that order and do, now I am giving the result as B at this common center is root of B1 squared plus B2 squared plus or minus 2B1 B2 cos theta. When do we get this positive or negative convention? That also I am now here writing, because I have already used it by right hand and drawn the vectors. And in the case of same order current, both P and Q carrying currents in same order, both clockwise, both anti-clockwise, then we have to use the positive sign. Then it becomes B1 square plus B2 square plus or minus plus 2B1 B2 cos theta. Whereas both P and Q carrying, yes, opposite order, currents in opposite order, one carrying clockwise, the other carrying anti-clockwise, then we will get it as root of B1 square plus B2 square minus 2B1 B2 cos theta. In the case of theta being 90 degrees, whether they are carrying parallel currents or anti-parallel currents, it does not matter. The result will be root of B1 square plus B2 square. Magnetic induction, circular conductor, two different points, comparison, one such example with simplification I am showing you. Circular conductor, radius given to be 10 centimeter, it says for an axial point, the induction is 1 by 8 times as compared to the induction at its center. Now the question is find the distance of axial point. Now just go through your notebook and find this result. B at axial point compared with the center, then this is 1 by 1 plus x squared by r squared, everything rises to 3 by 2, x is the distance of axial point, remember? Therefore now it is going to be 1 by 8, 1 by 8. Therefore even now simplification I show you, I will take this, so this becomes 8 is equal to, then this is 3 by 2, further simplification I am showing. This is 3, right? Therefore I am taking cube root. When I take the cube root, it will be 1 plus x squared by r squared, and it will be 1 by 2. Therefore cube root will be 2 here. Now again, how to remove this 1 by 2? How to get rid of that 1 by 2 index? Again square. Then you will get it as 4 is equal to, 4 is equal to, yes, r square plus x squared by r square. R square plus x squared by r square will be the result. Therefore this is 4r square minus r square. Therefore write 3r square is equal to x square, and x is equal to root 3 times r will be the answer. And r is going to be 10 centimeter, like that. So your simplification techniques are very important. Let us take one more case of magnetic induction produced by a conductor of different geometry. I have considered the case of arc-shaped conductor carrying current. The terms with regular meaning, I for current carried by the conductor or for the radius. Arc-shaped. Suppose this is an arc and this is the center of the arc and R is the radius carrying a current I. Again order again either clockwise or anti-clockwise. See the center. Now we are writing for induction at the center of the arc. For CET and NEET we are asked only at the centers. Induction at the center is equal to mu naught I theta by 4 pi r is the expression. Now here, what is this theta? Now theta is the angle made by the arc. So this is what is the angle of the arc theta at the center. So theta is the angle of the arc at the center to be substituted always in radian. Always in radian. So this is our expression. And what about the direction? Same as the right hand rule. Order of the curl of the fingers representing order of the current and thumb shows the direction of magnetic induction at the center. Now, to show you one example and to avoid a kind of confusion, I am telling you, suppose for semicircular conductor, semicircle means theta is equal to 180 degrees, right? So these numbers should not be used in degrees, therefore we will convert it to pi radians. Therefore now B at C is equal to mu naught I pi by 4 pi r. This is what is mu naught I by 4r. Even for any other arcs of different angles, please do remember, you substitute angle in radians only. Now you also see that here B at C proportional to theta, right? B at C proportional to theta is an important result. See, for half circle, semicircular conductor, you got mu naught I by 4r. Again you can see no pi term in the denominator, right? Last time also we have told and stressed a point that straight conductor, circular conductor, please make sure without any confusion. No pi term, 4r for circular. For circular conductor, what was the answer? Yesterday you got mu naught I by 2r. Why it was 2r in the denominator, which is double? Because of this reason you see B at C proportional to theta. This is how. Now the point is we have straight conductors, circular conductors, arc-shaped conductors. So examples are now, next examples will be based on the combination of these conductors. We are given a system which is with different shapes, and how to calculate the net induction at the point of observation will be our next session. Thank you.